us go through this question straight away. Copper is a transition element and has atomic number 29. Complete the electronics configuration for the copper atom and copper ions in the +2 oxidation state. So what is atomic number? It is actually proton number. Proton number means there are 29 protons. So 29 protons means 29 electrons also when they are atom. Atom is neutral. The number of protons is equal to the number of electrons. Okay, so they put argon here. So we need to know argon has 18 electrons. 18 electrons. So this one means 29 electrons. And here 18 electrons. So which 18 electron is like? It's like, the argon is actually 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so let's double confirm by adding up. 2 plus 2, 4, 4 plus 6, 10, 12, 18. So this is the 18 electrons. Okay. Now after 3p6, you have to write down already. So the cut short for you, the front part no need to write down. But after 3p6, so it's supposed to be 4s followed by 3d. But we still put 4s at the back, followed by 3d. Okay, so copper. Imagine 29 minus 18. 29 minus 18, we still have 29 minus 18, we still have 9. We still have 9. So if you have 9, right, if we follow normal way, we should fill up 4s first. So you fill up 2 electrons in 4s, then, just now we said we have 9 electrons, right? After using 2, we still have 7. 29 minus 18 is 11. 11. So 11 minus 2, we still have 9. So if we follow the conventional way, it will be 3d9 and 4s2. But if you still remember the theory, where that time we said, if there are lack of 1 to be fully filled, it is possible for 1 electron from 4s2 to shift to the 3d9 to make it fully filled and more stable. So because of that, we have to put 3d10 here and 4s1 here. Okay, so that is copper atom. And then copper ions, positive 2 oxidation state, that means you have to remove 2 electrons. So one from here, another one from here. So it becomes 3d9. So part B, the following equilibrium exists between 2 complex ions of copper in the positive 2 oxidation state. So you can see here this equation again, and name the type of reactions occurring here. So this is ligand exchange. Chloride is the ligand, a more powerful ligand. H2O is the weaker ligand. So the more powerful ligand replace the weaker ligand. So that is ligand exchange. Ligand exchange. Okay, now part 2, state the colors of these 2 complex ions. So this one we learned last week under copper chemistry. So now I just put the answer for you. You can always refer back to the notes. Blue, green. Part 3, state the shape of the CuCl4 2 minus, the shape. Okay, so this is tetrahedral shape. Tetrahedral shape. 4 ligand. 4 ligand, always think of either it is tetrahedral or square planar. So why this one we choose tetrahedral, we don't choose square planar? Because normally square planar is for nickel and platinum. If they are nickel platinum, you may try square planar. So if they are not nickel platinum, you just use tetrahedral. Okay, so let's move on. Put a short note here. Nickel, platinum, square planar. Okay, part 4. Write the expressions for the stability constants for these species. Okay, so how we write? We put product, but we don't want water. So we put product, Cu, Cl4, 2 minus. Okay, I think I better put the charge inside. 2 minus. Okay, over Cu, H2O6, 2 plus, Cl minus, power 4. Okay, so that is the case stability, case step. So part C, copper also form the complex ion CuNH32, H2O4, and CuEn, H2O4, 2 plus. So these are the other complex ion where En is the bidentate ligand, ethane 1,2-diamides. Okay, so these are the equilibrium equations. CuH2O6 2 plus 2 NH3. You know NH3 is a more powerful ligand. H2O is the weakest. So ligand exchange happens here. That's why the NH3 go inside. That's the first one. And then CuH2O6 2 plus En. Then you can see the En go in also. En go in, and 2 of the water molecule come out. So it seems like these two are more or less same situation. It's like they kick out 2 H2O and they replace with the corresponding ligands that we discussed here. Okay, they replace with NH3, 2 of them for this, and this one they replace with En. Okay, so similar situation. Now, what they ask now, what is meant by the term bidentate ligands? Bidentate, that means 2 lone pair. So we just explain accordingly. A species that contains 2 lone pairs that each form a coordinate or dative bond. Okay, so let's move on. Okay, now this is the application part. Part 2. In part 2, they give us values for the case step. The top one, 10 to the power of 7. The bottom one, 10 to the power of 10. So the idea here is the greater the case step, the more stable the complex. So that means the bottom one is more stable. So let us label it first. This is more stable. Okay. What do these case step values tell us about the relative positions of equilibria 1 and 2? Okay, so of course, if you know the concept of more stable, that means when we compare these equilibria 1 and 2, right, the second one is more stable, meaning that the position is more to the right. So we just need to write down in this way. So we say equilibrium 2. So if you're wondering why equilibrium and just now equilibria, so equilibria is the plural and equilibrium is the singular. So equilibrium 2 lies more to the right hand side. Okay, showing that the complex is more stable. And part D, nickel form the complex ion nickel En3 2 plus, in which it is surrounded octahedrally by 6 nitrogen atoms. Okay, name the type of stereoisomerism displayed by nickel En. Okay, so what happened here is it is like this. Let's say maybe I draw out first, as they ask you to draw. So after I draw out, then you can imagine why the answer is that particular answer. So I draw first. If you still remember En, right? So En is actually the one that, which is here. Okay, is in the question itself. En is ethane 1,2-diamide, H2N. The lone pair is at the nitrogen here. CH2, CH2, and H2. So another lone pair at the second nitrogen. So this is bidentate. So it donates 2 lone pair to the central metal ions. So it looks like this. It has 6 lone pair altogether because there are 3 En. So nickel. Okay. So 2 from this En. The other 2 from this En. So be aware of the arrow that I draw. When I draw dotted arrow, that means this is towards the back of the paper or the screen, to the back of the screen. This is to the front of the screen. Okay, they are front and back. So we try to put it in 3D. Okay, now we continue. So this is to the back and then to the front. En 2 plus. Okay. So meaning that one En with 2 nitrogen, 1 nitrogen donate lone pair up from the top positions, and another nitrogen donate lone pair from the back positions. This En, one donate from the bottom, another one donate from the front. This En, one donate from the front, and another one donate from the back. Okay, so what kind of stereoisomers? So this is actually the optical stereoisomer. Optical. So when we say optical, that means to draw the stereoisomer, whatever on the right, you shift it to the left. So something like this, shift it to the left. So now this is the back, the front. So the other one is, just now this is top and left. Now it's top and right. From the back also. Okay, now one more. Bottom and front. Okay. 2 plus. So these are the optical isomer, and because of that, D part 1 is optical isomerisms. Okay, so this one we settle.